Okay, let's go take a look at 12.2. Some of you asked some questions about those problems. And we did one, but a lot of times it helps to do multiple problems from this section, from each section. But here's kind of the scenario. We have one population here, and we take one sample. And this is count data, frequencies. Study was conducted to investigate the relationship between the colors of helmets: black helmet, white helmet, yellow or orange helmet, red helmet, blue helmet, all these different colors, worn by motorcycle drivers, and whether they are injured or killed in a crash. So all of these individuals were involved. Let's see, and whether they are injured. All right, so I guess they were all involved in a, crash of some sort. And so there's two different outcomes. If they're involved in a crash of some sort, they could walk away without any injuries, not be injured, or they could be injured seriously or even killed. So there were 8 individual motorcycle drivers who were injured or killed while wearing a yellow or orange helmet. There were 170 motorcycle drivers who were wearing a red hat and were not injured. So these are frequencies. These represent individuals. And you have to come to grips with the fact that the numbers that you see does not mean that we're dealing with numerical data. In fact, in this case, it's just the opposite of that. This is not numerical data. These are not individual data values like those differences we saw in the first example, like footwell intrusions, where we actually get the tape measure out and we measure how far the engine parts came into the footwell. That's not these. This is 491 folks, and they had all this injury data, and they focused in on 2 columns. What was the color of the helmet? Red, blue, black, and so on. When someone responds with the color of a helmet like this, these are not numbers. And the other thing is the injury status. So was the individual injured or not? And if you look at the raw data there, it's just going to be a field, and the responses are not injured, not injured, not injured, killed, 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 injured, killed, not injured. Those are all, again, categorical responses. So there's 2 categorical responses, and each one of these represents the number of individuals. So it's a lot of folks that drove motorcycles that are included in this data. Okay, so that's kind of the overview. And now we want to know if there's a relationship of some sort between the type of helmet someone's wearing and whether or not they get injured or not, the injury status, we say. The way that we can see if there's a relationship is to calculate the conditional proportions. The conditional proportions, this was the section 4.4, where all you did in that section was calculate conditional proportions. And then if we want to know if those observed differences that we observe from the sample data are statistically significant, we then have to go and run the chi-squared test to see that. Okay, so it helps to do row totals and column totals. You need it for the expected values. And so let's go ahead, add up those 2 numbers. These are called the column totals, and these 2, and do it for every column. And then if you add all the way across, add those 5 numbers, you're going to get the total in the sample. 1,579 motorcycle drivers that were involved in a crash. Similarly, if you add up all the numbers in the row, you would find the total number that were not injured. And then if you add all the injured and killed, you get to 429. And then these two numbers also add up too. Yes. Now, if we, now we're coming down here. Now, if we want to use the color of the helmet as the independent variable, then we're going to calculate our conditional proportions, not using these numbers, but rather using the column totals. So that means we would have to divide those two numbers by 704, these two numbers by 489, okay, I got another question here. When doing the t-test on the calculator, what is mean sub 0? It's always that number that appears in the null hypothesis. And for this particular test, every single time, mu0 is that number. Back in chapter 10, when we were doing a t-test, when claims were made about a single population mean, this number varied quite a lot. You know, sometimes it's 12, sometimes it's 40, sometimes lots of other things.
Posted videos, I don't even follow. I don't even know how he was watching my stories, because I don't think he follows me either. I don't even know who he is.
Yeah, so just be careful when you're that your mute is on, because if it's not on and you're talking elsewhere, we get to hear everything of that's going on in the room, and you've probably seen some memes about that. Kendall, is that good? Does that answer your question? Okay. Back to this one. All of these we're going to divide by 39. These we're going to divide by 240. And these we're going to divide by 107. So, you know, sometimes we're going to be dividing by 1150 all the way through. If the injury status was the independent variable, then we would divide by 1150, all these numbers. And we would divide all these numbers by 429. So, all right, so these are the conditional proportions. So take 491 and divide by 704. And if you do that, you get 0.697. And that means that this number is going to be 1 minus that. Or if you take 213 and divide by 704, you're going to get the 0.303. 377 divided by 489, 0.771. And 1 minus that is 0.229, or 112 divided by 489. 31 divided by 39 is 0.795. And here, 8 divided by 39 is 0.205. And so on. And this is what you should get for the rest of them. All right, so this is the table for conditional proportions. This one up here, this is the frequency data. Which is our sample data, which are our observed data. What we observed from our one sample. Now there's another table that that you could construct, or you could be asked to construct, and that's the one with the expected values. But in part C, all I asked for was the expected count in the cell of the first table corresponding to the observed count of 377. So what's the observed? So white helmet and not injured. What's the expected count? Well, here's what we do. Sometimes the notation is the expected value in row 1, column 2. All right, so we're going to take the row total of the first and then multiply that by the column total and divide by the table total, or the total sample size. So the row total is 1150. For that data value, it's in this row, so the row total is 1150. This data value is in this column, so the column total is 489. So you multiply those two numbers and you divide by the table total, which is the 1579. So we'll just go ahead and calculate that. And we get 356.143. Now, since there are 1, 2, 3, 4, 5 times 5, 10 different cells, you're actually going to have 10 different expected values. But this one just asks you to calculate one of those. Remember that the expected counts will appear in matrix B after you run the chi-square test. All right, so here we have an alpha, that injuries are independent of helmet color. All right, so here's the claim, and the claim is independence. Be sure to identify the test statistic. In this case, it's the chi-squared test statistic and the p-value of the test. And then write a summary sentence describing what the evidence from the sample suggests. All right, let's take a look at these sample proportions just to see if we do find a statistically significant result, if we do find that we reject the null hypothesis in favor that the two variables are dependent, which means that there is a relationship. What is the relationship if there is one? And what you do is you compare these numbers in the row, because we divided by the row total or the column totals here. We then want to compare the numbers for each row and see if they're different. And one thing you can do here is just to pick out the biggest one and the smallest one. And if you compare those two, this is about 80% and this is about 70%. Between these two, there's a 10 percentage point difference. And remember, these are proportions. So you can easily convert proportions into percentages, and you'd say something like this for this number. When a black helmet was worn, about 70% of those involved in an accident on a motorcycle were not injured. However, when a yellow or orange helmet was used, and this percentage is very close to this one. So when a yellow or orange helmet was used, full 10 percentage points higher, 80% of those riders were not injured. And then you can go down to the next row. Whereas, we'll just pick out the largest one and the smallest one. Whereas When a black helmet is worn, about 30% of the motorcycle riders involved in a crash were injured or killed, compared to only 20% for those wearing a yellow or orange helmet. So we do see a difference here. And there are other differences you can observe, but one that you can pick out is just the smallest compared to the largest. So if we do find a statistically significant relationship here, and we do reject the null hypothesis, then we're going to write up this in our concluding statement. All right. So let me just quickly go through the rest of this. The null hypothesis and the alternative hypothesis doesn't ask for it here, so we don't need to really do this, but the null hypothesis is always a statement that there's no difference, in this case independent, not related to one another, no association, injuries. Okay, so variable 1, injury status, and variable 2, helmet color, are independent. And here's your claim. And just repeat that, but just say that the two variables are, if they're not independent, they're dependent. Dependent means that a relationship exists. Independent means no relationship exists, or at least not a statistically significant one. So that's a big difference in the test that we've written for chapter 12. We write it in words, we're not using any variables. So the good news is that you don't have to define any variables because we don't use variables for this test. All right, so we've got alpha. All right, this is new as well. I described it last time, but when you're going to run this test, it's the chi-squared test. It appears where all the other tests appear, in the test menu of the stats menu of the calculator. And you want option C, which is chi-squared test. And these will always stay the same. You want to put your observed values in matrix A, and if that's all you do, and then you run this test will insert all the expected values into matrix B. So, and the observed values are what you're going to see up here in your frequency data, the sample data, the observed data. That's this stuff in here. So you want to create a matrix to contain all of this frequency data right here. And in this rectangular grid of numbers, which is the definition of a matrix, a rectangular array of numbers, we have 2 rows, and we have 1, 2, 3, 4, 5 columns. So the dimensions of the matrix are 2 by 5. So let's go enter in those 10 numbers here, 2 by 5, just like this, in a matrix. So here's the matrix menu of your calculator. Hit the second key to get it. All right, we want to go over to edit that matrix. Currently it's a 3 by 2, and we want a 2 by 5. So we'll edit this matrix, and right at the top, we'll hit 2 and then enter, and then 5 and then enter. And this very first row gives us the dimensions of the matrix. So you can see the 2 rows, and this dot, dot, dot means that there's more stuff over there. All right, let's enter in row by row these 10 numbers: 491, 377, 31, 170, 81. When you hit enter, it comes back to the first row. 213, 112, 8, 70, and 26. Now, once you have all of those numbers up here entered in, you'll want to quit out of the matrix menu and go back to the home screen. So right there's the quit button. If you want to take a look at your matrix, you can go to the matrix menu again. And then instead of editing, just select matrix 1. So matrix A goes to your home screen. And there it is. And you can review it to make sure that you typed in all the numbers correctly. All right, now let's go look at matrix B. Now matrix B, it says here that it's a 3x2 matrix. If I type it in, well, there it is. Looks like it just has 3 rows. 2 rows, 3 columns. 3 rows, 2 columns. And that's not what we want. Those clearly are not the expected values. We calculated 1 in part B there, and we don't see that number anywhere. So the expected values are not calculated automatically. In order for you to tell the calculator to calculate those expected values, you have to run the test, the chi-squared test. So go to Stat, and then over to the tests, and then scroll down to that chi-squared test. Right there. Now, even though we didn't put the expected value, we didn't calculate them. We only calculated 1, and we'll go check to make sure that that one's correct. Well, we only calculated 1 of them, and I told you there were 10 of them we would have to calculate. But we're going to avoid calculating those, and we'll let the calculator calculate all those. So I'm just going to come down here. And before I do that, I just want to remind you that the degrees of freedom for this test is the number of rows minus 1 times the number of columns minus 1. So 2 minus 1 times 5 minus 1, 1 times 4. So, and I wanted to do it before that we ran this calculator function because one of the pieces of output from the chi-squared test calculator function is the degrees of freedom. Okay, so the output here, the test statistic is the first number that's reported. And then you've got the p-value, and then there's the degrees of freedom. So let's write that down. We have the chi-squared test statistic. And that's 9. All right, does that test statistic look better?
Yeah.
Okay, 9.688. And the p-value is, looks like it's a 6 instead. So that one little mistake that I made. All right, now I should be able to go back and select matrix B and see the correct expected value there. Okay. P is equal to 0.046, alpha is equal to 0.10, and the P is less than alpha, so we're going to reject the null hypothesis. So we're rejecting the null hypothesis in favor of the alternative that says that the 2 variables are somehow related. They're dependent. So we're rejecting the claim. So this is another one where we're going to have to say something like, there is evidence to reject the claim. That injury status and helmet color are independent. All right, I usually will, I mean, you know, that kind of gets at it, but I usually ask you in this test to go further. So a lot of times I'll ask a question like you'll see in part D there. Should motorcycle drivers choose helmets of a particular color? If so, which color? Okay. Probably not, because if someone buys a yellow or orange helmet, they still have to do something else. They have to put themselves in a tough situation while driving. I don't think that you know, we can talk about, you know, the reason why more people are not injured when they when they wear a yellow or orange helmet. And while more, you know, here seems like a higher percentage of motorcycle riders when they're in crashes are injured or killed when they're wearing a black helmet. That doesn't mean that a black helmet causes the death or the injury. So there's probably some other variables out there. Unless the manufacturer of these helmets are making the yellow and orange ones safer for some reason, but I doubt that that's happening. But for this one, we're going to go on to say the data suggests that wearing the yellow or orange helmet leads to a lower percentage of injuries or deaths than wearing a black helmet. This one asks for the classical approach. You've got degrees of freedom is 3. So you should be able to find this number from the chi table. And then here's the test statistic. It hovers out here in the reject region. So we're going to reject the null hypothesis that there's no relationship between age and communication preference. So there must be a relationship. And then here's how I wrote up that relationship. The younger cohort prefers using the cell phone and text messages more than the older cohort. And you could turn it around and say that it's not that they prefer it more, it's that they prefer it at a higher rate than the older group. So this is the chi-squared test in 12.2. And this table right here, calculating these conditional proportions, is what you're going to be doing in 4.